All right, we're looking at the air homework packet, starting with the air around you. Just a reminder to take a look at these key concepts, the reading preview that they have over here. It always has really good information for you to take a look at before you start doing the reading, because that way you know what the important things are to pay attention to. So what is the composition of Earth's atmosphere? What is Earth's atmosphere made up of? And how is the atmosphere important to living things? So those are two things that you're supposed to be able to describe after you've done this reading. Keywords to look out for: weather, atmosphere, ozone, and water vapor. All right, let's take a look. The sky is full of thick, dark clouds. In the distance, you see a bright flash. 30 seconds later, you hear a crack of thunder. You begin to run and reach your home just as the downpour begins. That was close. From your window, you look out to watch the storm. Does the weather where you live change often, or is it fairly constant from day to day? Weather is the condition of Earth's atmosphere at a particular time and place. But what is the atmosphere? Earth's atmosphere is the envelope of gases that surrounds the planet. To understand the relative size of the atmosphere, imagine that Earth is the size of an apple. If you breathe on the apple, a thin film of water droplets will form on its surface. Earth's atmosphere is like that water on the apple, a thin layer of gases on Earth's surface. Taking a look at this chart here is probably helpful before you go into the reading. So I always try to look at charts and pictures before I do the reading, because I think that sometimes that stuff just helps you absorb it a little bit better than reading like sentences do. So taking a look here, it's talking about gases in dry air. So water vapor, for example, is a gas, but they're not counting that as a part of dry air because that's considered wet air because it's water vapor. Okay, so if you're talking about every gas in the atmosphere except for water vapor, you're talking about like 78% nitrogen. So that's like 3/4-ish, right? A little more. 21% oxygen. So a lot of students often think that oxygen is the most prominent gas in the atmosphere because that's what we breathe. But actually, it's only about a quarter. It's a little less than a quarter of the atmosphere. And then all the other gases make up 1%. So our atmosphere is mostly nitrogen, some oxygen, and then very little amount of all of these other gases. So if you take a look here at this chart, argon, carbon dioxide, which I'm sure you've heard a lot about and we'll learn more about in our climate change unit, neon, helium, methane, krypton, and hydrogen. These are all gases in the atmosphere. And if you look here, the percent by volume, argon makes up almost that whole 1%, 0.93. And then if you add up all of these other things together, that's what gives us the last 0.1, a little less than that, right, percent. So it's pretty amazing to think. I know you probably think of carbon dioxide as being probably as much as these other gases, but really it's just a very small amount in the atmosphere. And so it makes a big difference, though. All right, let's read. Composition of the atmosphere. The atmosphere is made up of a mixture of atoms and molecules of different kinds. An atom is the smallest unit of a chemical element that can exist by itself. Molecules are made up of two or more atoms. So atoms are the very smallest part, and molecules are combinations of atoms. Earth's atmosphere is made up of nitrogen, oxygen, carbon dioxide, water vapor, and many other gases, as well as particles of liquids and solids. So anytime you see a bold sentence like that, it's probably something worth writing down. Nitrogen. As you can see in Figure 1, nitrogen is the most abundant gas in the atmosphere. Remember, that was about 78%. It makes up a little more than 3/4 of the air we breathe. Each nitrogen molecule consists of 2 nitrogen atoms. Oxygen. Even though oxygen is the second most abundant gas in the atmosphere, it makes up less than 1/4 of the volume. Plants and animals take oxygen directly from the air and use it to release energy from their food. Oxygen is also involved in many other important processes. Any fuel you can think of, from gasoline in a car to the candles on a birthday cake, uses oxygen as it burns. Without oxygen, a fire will go out. Burning uses oxygen rapidly. During other processes, oxygen is used slowly. For example, steel in cars and other objects reacts slowly with oxygen to form iron oxide, or rust. Most oxygen molecules have two oxygen atoms. Ozone is a form of oxygen that has 3 oxygen atoms in each molecule instead of the usual 2. Have you ever noticed a pungent smell in the air after a thunderstorm? This is the odor of ozone, which forms when lightning interacts with oxygen in the air. Pretty cool. Check this out. Water vapor in the air. There is very little water vapor in the air over the desert where this lizard lives. In the tropical rainforest where a frog lives, there is as much as 4% of the air may be water vapor. So, on a humid day, you can kind of feel the water vapor in the air, right? Makes it feel a little hotter. All right, carbon dioxide. Each molecule of carbon dioxide has 1 atom of carbon and 2 atoms of oxygen. Carbon, di, meaning 2, oxide, which stands for oxygen. Carbon dioxide is essential to life. Plants must have carbon dioxide to produce food. When the cells of plants and animals break down food to produce energy, they give off carbon dioxide as a waste product. When fuels such as coal and gasoline are burned, they release carbon dioxide. Burning these fuels increases the amount of carbon dioxide in the atmosphere. Oxygen and nitrogen together make up 99% of dry air. Argon and carbon dioxide make up most of the other 1%. The remaining gases are called trace gases because only a small amount of them are present. So far, we have discussed the composition of dry air. In reality, air is not dry because it contains water vapor. Water vapor is water in the form of a gas. Water vapor is invisible. It is not the same thing as steam, which is made up of tiny droplets of liquid water. Each water molecule contains 2 atoms of hydrogen and 1 atom of oxygen. The amount of water vapor in the air varies greatly from place to place and from time to time. Water vapor plays an important role in Earth's weather. Clouds form when water vapor condenses out of the air to form tiny droplets of liquid water, or crystals of ice. If these droplets or crystals become heavy enough, they can fall as rain or snow. Particles. Pure air contains only gases, but pure air exists only in laboratories. In the real world, air also contains tiny solid and liquid particles of dust, smoke, salt, and other chemicals. You can see some of these particles in the air around you, but most of them are too small to see. Importance of the atmosphere. Remember, this is one of the things at the beginning of the section they said that you should be able to answer. Earth's atmosphere makes conditions on Earth suitable for living things. The atmosphere contains oxygen and other gases that you and other living things need to survive. In turn, living things affect the atmosphere. The atmosphere is constantly changing, with gases moving in and out of living things, the land, and the water. Living things need warmth and liquid water. By trapping energy from the sun, the atmosphere keeps most of Earth's surface warm enough for water to exist as a liquid. In addition, Earth's atmosphere protects living things from dangerous radiation from the sun. The atmosphere also prevents Earth's surface from being hit by most meteoroids or rocks from outer space. You could always kind of look through these sort of Section 1 assessments, even though you've probably been given something like this as homework in the past. You don't actually have to write it down, but if you can go through and you're able to answer most of these questions, then you know you've understood the reading. All right, let's move on to air pressure. So let's start here by checking out the reading preview. The key concepts: what are some of the properties of air? What instruments are used to measure air pressure? And how does increasing altitude affect air pressure and density? And then these are the key terms that they want you to know. So density, pressure, air pressure, barometer, not barometer, barometer. And then there are 2 kinds, a mercury and an aneroid barometer, and then altitude. All right, let's start. The air is cool and clear, just perfect for an overnight hiking trip. You've stuffed your backpack with your tent, sleeping bag, stove, and food. When you hoist your pack onto your back, its weight presses into your shoulders. That pack sure is heavy. So corny. By the end of the day, you'll be glad to take it off and get rid of all that weight. But here's a surprise. Even when you take off your pack, your shoulders will still have pressure on them. The weight of the atmosphere itself is constantly pressing on your body. Properties of air. It may seem to you that air has no mass, but in fact, air consists of atoms and molecules which have mass, so air must have mass. Because air has mass, it also has other properties, including density and pressure. Density. The amount of mass in a given volume of air is density. Well, that's the density of air. The amount of mass in a given volume is density. You can calculate the density of a substance by dividing its mass by its volume. If there are more molecules in a given volume, the density is greater. If there are fewer molecules, the density is less. Pressure. The force of pushing on an area or surface is known as pressure. The weight of the atmosphere exerts a force on surfaces. Air pressure is the result of the weight of a column of air pushing down on an area. The column of air extends upward through the entire atmosphere. So they're saying, look at figure 4, that's this here. So imagine this is the backpacker, right? And you have to think about all the air all the way up until the end of the atmosphere meets outer space. All of that air is pushing down on that person and anything underneath it. The atmosphere is heavy. The weight of the column of air above your desk is about the same as the weight of a large school bus. So why doesn't air pressure crush your desk? The reason is that the molecules in air push in all directions, up, down, up, and sideways. The air pushing down on top of your desk is balanced by air pushing up on the bottom of your desk. Air pressure can change from day to day. A denser substance has more mass per unit volume than a less dense one. So denser air exerts more pressure than less dense air. So think about cold, dense air sinking down. That's going to put more pressure than warm, less dense air rising up. That's going to be less pressure. Okay, measuring air pressure. A barometer is an instrument that is used to measure air pressure. Two common kinds of barometers are mercury barometers and aneroid barometers. Figure 5 shows the way a mercury barometer works. A mercury barometer consists of a glass tube open at the bottom end and partially filled with mercury. Mercury, by the way, is super dangerous and can cause cancer and craziness, so we don't really use mercury barometers anymore. Side note. The space in the tube above the mercury is almost a vacuum. It contains very little air. The open end of the tube rests in a dish of mercury. The air pressure pushing down on the surface of the mercury in the dish is equal to the pressure exerted by the weight of the column of mercury in the tube. When the air pressure increases, it presses down more on the surface of the mercury. Greater air pressure forces the column of mercury up higher. At sea level, the mercury column is about 76 centimeters high on average. So here, look, they're basically saying that the air pressure pushes down on this, right, which is then going to push the mercury up the tube. So higher air pressure is going to push down more here, so it's going to go higher up the tube. Lower air pressure is going to be pushing less here, so it'll be lower in the tube. Okay, that's how a barometer works. Aneroid barometers. If you have a barometer at home, it is probably an aneroid barometer. The word aneroid means without liquid. An aneroid barometer has an airtight metal chamber, as shown in figure 6. We'll go to that in a second. The metal chamber is sensitive to changes in air pressure. When air pressure increases, the thin walls of the chamber are pushed in. When the pressure drops, the walls bulge out. The chamber is connected to a dial by a series of springs and levers. As the shape of the chamber changes, the needle on the dial moves. See this? As air pressure pushes on it, it'll change the direction that the needle points. So basically, it's just a really sensitive metal that is acting the same way that the mercury does here, just it's not liquid, it's metal. Units of air pressure. Weather reports use several different units for air pressure. Most weather reports for the general public use most weather reports for the general public use inches of mercury. For example, if the column of mercury in a mercury barometer is 30 inches high, the air pressure is 30 inches of mercury, or just 30 inches. National Weather Service maps indicate air pressure in millibars. 1 inch of mercury is approximately 33.87 millibars, so 30 inches of mercury is approximately equal to 1,016 millibars. Altitude and properties of air. At the top of a mountain, the air pressure is less than the air pressure at sea level. Altitude, or elevation, how far you are above sea level, the average level of the surface of the oceans. So sea level, they're saying, is the average level of the surface of the oceans. That was confusing for me. I think that was a very confusing sentence. So altitude is how high something is above sea level. Air pressure decreases as altitude increases. As air pressure decreases, so does density. Altitude affects air pressure. Imagine a stack of books. Which book has more weight on it, the second book from the top or the book at the bottom? The second book from the top has only the weight of one book on top of it. The book at the bottom of the stack has the weight of all the books pressing on it. Air at sea level is more like the bottom book. Sea level air has the weight of the whole atmosphere pressing on it, so air pressure is greater at sea level. Air near the top of the atmosphere is like the second book from the top. There, the air has less weight pressing on it and thus lower air pressure. So the higher up a mountain you go, for instance, the less air pressure there is. Altitude also affects density. As you go up through the atmosphere, the density of the air decreases. This means the gas molecules that make up the atmosphere are farther apart at high altitudes than they are at sea level. If you were near the top of a tall mountain and tried to run, you would quickly get out of breath. Why? The air contains 21% oxygen, whether you are at sea level or at the top of a mountain. However, since the air is less dense at high altitude, there are fewer oxygen molecules to breathe in each cubic meter of air than at sea level. So basically, even though it's the same percentage, there's actually less at the top of a mountain. So, you would become short of breath quickly at high altitudes. I think the picture really helps in this, right? They're saying these little dots are all the oxygen down here at sea level, and these dots are all the oxygen up here at the top of the mountain. Even though they're looking at the same amount, it's still 21% of all of the air molecules that are in that amount. Does that make sense? Okay, last section, air quality. Let's take a look here. What are the major sources of air pollution? What causes smog and acid rain? And what can be done to improve air quality? Terms you're looking for are pollutants, photochemical smog, fancy, and acid rain. As you are reading this page, you are breathing without even thinking about it. Breathing brings air into your lungs, where the oxygen you need is taken into your body. But not everything in the air is healthful. You may also breathe in tiny particles or even small amounts of harmful gases. If you live in a large city, you may have noticed a brown haze in the air. Even if you live far from a city, the air around you may contain pollutants. Pollutants are harmful substances in the air, water, or soil. Air that contains harmful particles and gases is said to be polluted. Air pollution can affect the health of humans and other living things. Figure 12 identifies the effects of some pollutants. So carbon monoxide comes from fossil fuels, and that is actually potentially fatal. It could kill you if you breathe in too much carbon monoxide. Ozone can actually, though, it actually helps block out ultraviolet rays, which cause sunburn. So we do need a little bit of ozone. Not all ozone is bad. Okay. Sources of pollution. Some air pollution occurs naturally, but many types of air pollution are the result of human activities. Many natural processes add particles to the atmosphere. Forest fires, soil erosion, and dust storms release dust into the air. The wind carries particles of mold and pollen. Erupting volcanoes spew out clouds of dust and ash along with poisonous gases. So these are all natural sources of pollution. Now, this section is going to talk about human activities and how they contribute to pollution. So human activities such as farming and construction can send soil and dust into the air. But most air pollution is a result of burning fossil fuels such as coal, oil, gasoline, and diesel fuel. Almost half of this pollution comes from cars and other motor vehicles. Factories and power plants that burn coal and oil also release pollution. When fossil fuels burn, they release both particles and gases. When people burn wood or coal, particles of soot enter the air. Soot gives smoke its dark color. All fossil fuels contain hydrocarbons, compounds made of hydrogen and carbon. As fossil fuels burn, some hydrocarbons do not burn completely and escape into the air. Burning fossil fuels produces a variety of pollutants, including carbon monoxide, nitrogen oxides, and sulfur oxides. Smog and acid rain. High levels of air pollution decrease the quality of the air. The burning of fossil fuels can cause smog and acid rain. 100 years ago, London-type smog, 100 years ago, the city of London, England, was dark and dirty. Factories burned coal, and most houses were heated by coal. The air was full of soot. In 1905, the term smog was created by combining the words smoke and fog to describe this type of air pollution. Typically, London-type smog forms when particles in coal. Wow, I'm having trouble with this sentence. Let me start over. Typically, London-type smog forms when particles in coal smoke combine with water droplets in humid air. Today, people in London burn much less coal. As a result, the air in London is now much cleaner than it was 100 years ago. There's a great story that we'll talk about in the genetics unit too that talks about the effects that had on wildlife in the area, in particular moths and the color of moths. Photochemical smog. Fortunately, London-type smog is no longer common in the United States. Instead, many cities today have another type of smog. The brown haze that develops in sunny cities is called photochemical smog. The photo in photochemical means light. Photochemical smog is formed by the action of sunlight on pollutants such as hydrocarbons and nitrogen oxides. These chemicals react to form a brownish mixture of ozone and other pollutants. Recall that ozone in the stratosphere blocks ultraviolet radiation, thus protecting living things on Earth. But in the troposphere, ozone is a pollutant that can irritate the eyes. So they're saying that ozone higher up in the atmosphere is good, but in the troposphere, this bottom layer of the atmosphere where all weather occurs, it can actually be irritating to humans in their eyes, throat, and lungs. It can also harm plants and other living things and damage many materials. Acid rain. Another result of air pollution is acid rain. Rain is naturally slightly acidic, but rain that contains more acid than normal is known as acid rain. How does acid rain form? The burning of coal that contains a lot of sulfur produces sulfur oxides, substances composed of oxygen and sulfur. Acid rain forms when nitrogen oxides and sulfur oxides combine with water in the air to form nitric acid and sulfuric acid. There's a lot of chemical names. The biggest thing to understand is that it comes from the burning of coal, okay, and how acid rain is more acidic. Okay, that's what to focus on. Rain, sleet, snow, fog, and even dry particles carry these two acids to trees and lakes. Acid rain is sometimes strong enough to damage the surfaces of buildings and statues. It also harms lakes and ponds. Acid rain can make water so acidic that plants, amphibians, fish, and insects can no longer survive in it. Improving air quality. In the United States, the federal and state governments have passed a number of laws and regulations to reduce air pollution. The Environmental Protection Agency, EPA, which you hear a lot in the news, the EPA, it means the Environmental Protection Agency. They monitor air pollutants in the United States. Air quality in this country has generally improved over the past 30 years. The amounts of most major air pollutants have decreased. Many newer cars cause less pollution than older models. Recently built power plants are less polluting than power plants that have been in operation for many years. However, there are now more cars on the road and more power plants burning fossil fuels than in the past. Unfortunately, the air in many American cities is still polluted. Voluntary measures, such as greater use of public transportation in place of driving, could reduce the total amount of air pollution produced. Many people think that stricter regulations are needed to control air pollution. Others argue that reducing air pollution can be very expensive and that the benefits of stricter regulations may not be worth the costs. So we'll talk more about that in the climate change unit. All right, that is the reading for this section. Of course, you can always go back and look through the section to see if you can answer these questions, and then you'll know that you understood what you needed to.